This is what I wanted to show you about Flashpoint, and now we are getting a little bit more into a generic product, fuel testing by infrared analysis. First, I want to show you how this infrared analysis works and what it does in fuel analysis, how it's working with our IR vision, and what test methods we have and what they are. So if you look into fuels, be it the diesel fuel, jet fuel, or gasoline, you have really a complex mixture of different hydrocarbons. In spectroscopy, those components which you have there absorb a characteristic part of the radiation and thus can be detected. Among the many parameters, there are concentrations, components, which you see here, and components are typically oxygenates, ethers, aromatics, octane boosters, and other things. And then you have things that we call properties. Properties because they are not concentrations and not directly measured by infrared, but indirectly through correlation databases. With the exception of the density, we have a built-in density meter, but octane number, cetane number, vapor pressure, distillation point, flash point, even freezing point, those are all correlated properties which you can train into the instrument. And these many parameters are allowing you to characterize a fuel very good, and that's why it's widely used. It's relevant for everybody who deals with fuels, starting from the producers, like the refineries, biofuel producers, the blenders, transportation and storage operators, terminals, then of course the fuel outlets, gas stations, and all the consumers, be it simple car drivers, car manufacturers, or customers who buy bulk fuels like mining operators, the military, and so on. But also in QC laboratories and R&D laboratories, you see this analyzer very often. So how is infrared spectroscopy working? And there are basically 4 techniques which you can apply to disperse the radiation or the energy to see which characteristic energy was absorbed by the components which I've mentioned before. And each technique has unique advantages and limitations. The first and most simple technique are prisms. It's also the most cheapest ways, filters and prisms. The prisms only work around the visible range, but the filters are widely applicable from X-ray radiation up to very long wavelengths, infrared, far infrared, for example. Then you have grating mirrors. Grating mirrors are specially designed mirrors that, depending on the angle of reflection, are reflecting different energy bands of the radiation. They're also quite flexible and applicable over a wide range, but tend a little bit to glitches at certain wavelengths. Then very modern are quantum cascade lasers. The quantum cascade lasers have the advantage of high intensity. So if you just need very high intensity and need to look at the limited narrow energy band, then they are ideal. So the limitation is really that they have a very limited energy band you can use. The most flexible and widely applied technique is basically the Fourier transformation infrared spectroscopy, because it's very flexible. It applies an interferometer, like is shown here, and I will show you a little bit on the next slides. And the interferogram is then transformed to an absorption spectra by the mean of a Fourier transformation. So this is basically the setup of the Michelson interferometer in the FTIR system that we are using. Basically, you have a light source, incoming radiation, then a beam splitter. This is the heart, basically, of the interferometer, because it reflects one part of the light to a scanning mirror, which is moving back and forth, and the other part is going to a so-called fixed mirror. both radiations, when they come back, they combine, and depending on the phase shift that which you have introduced through the scanning mirror, you are getting here a different intensity of the radiation, and out of this intensity, the sample here is also absorbing their particular portions. And then you have a detector who is detecting the intensity, and basically the intensity is plotted versus the distance that scanning mirror is driving. And what you get is basically an interferogram. So the setup of our instrument is basically using 3 different cells. You see here the 100 micron cell, and here a 35 micron cell. In the first run, we are doing basically just a scan of the window. This is just a window to get a reference scan. And in the standard measurements, we are scanning through the 35 micrometer sample width. This is applicable for most fuels and samples. But for certain standards, we also need to use, especially for jet or diesel standards, the 100 micron cell. What you finally get after you transform your interferogram is an absorption spectrum, which can look like this on the screen of the instrument itself, or we have also a specially designed software where you can also work with the spectra. This is a representation of several spectra overlaid to each other. The range which we are using is really covering the typical range of the mid-infrared spectrum. We have a resolution of 3.8 centimeters, which is the ideal resolution, especially also for doing property predictions. The spectrum can be exported also to be used in other spectroscopic programs, and it's also possible to connect to this directly through an FTP access and download the spectrum. We have customers who are doing this. Now we have the spectrum, but how can you now get to the corresponding parameters? To get to the parameters which I've mentioned before, the concentrations or octane ratings and so on, we apply 5 different types of methods in the IR vision. And we differentiate direct methods, K-matrix, arithmetic methods, then the chemometrics, partial least squares, or the cluster analysis or nearest neighbor search, which I would rather call this. And corresponding parameters are pure components for the direct or the K-matrix. For the arithmetic means that it takes results and basically combines them arithmetically. And for the PLS, for the chemometrics, the property predictions are basically coming out. Direct method, how does it look like? Basically, the direct method is calibrating the height of a peak or the area of a peak to a certain concentration of a component. That's very simple and typically the state of the art or the classical domain of spectroscopy. But as mentioned, fuels are complex mixtures, and these direct methods work only if you have not overlapping peaks or very isolated peaks, like in diesel or jet fuel. Those are more featureless. But gasoline, for example, has a very broad mixture of different components, oxygenates. And here we are using the K-matrix. The K-matrix, for example, is using the individual spectra of the components, like they are shown here, as a calibration part. And this is then with a certain matrix operation tried to fit into the actual measured spectrum. And if you are fitting this into the sample spectrum, the fit parameters are proportional to the concentration of these individual components. So you can again get the concentrations, but even though you have a lot of overlapping peaks. So that's the good advantage of the K-matrix method. Chemometrics, the partial least squares, is applying a model, and the model needs to be trained into the instrument. So how does this training work in a very simplistic way? I just wanted to highlight you this little peak here, which could be one of the many features which we could track. And we have the spectrum of a typical gasoline. So now, if we are applying this spectrometer and we plot this peak height here against the property which we want to measure, then we can measure different gasolines, and we need to measure different gasolines, where especially this feature, this peak, is changing its height. And we see that this peak is changing the height with raising octane rating. I mean, it's a very simplistic way, of course, but it shows the principle of this PLS. And then you can fit basically a PLS model into this. So it's basically a regression analysis. What can you do with this regression analysis? Now, if you have an unknown sample, you can look at this peak height, and then you take the model, and you can basically take out the octane rating as a result based on this model. What's the nearest neighbor search or cluster analysis? This is a little bit dangerous, but we added it because many customers requested it, and our competitors also use this. But it's something where you have to be a little bit cautious, because what it's doing, it's basically not taking the model as a result, but it takes the nearest other sample which is in a database which it finds, and then reports the value of this particular sample it's finding, which is very similar to the one which you have measured in the ideal case. The cluster analysis or nearest neighbor search has, of course, some advantages if it's very difficult to establish a PLS model, like you see here, when you have very heterogenic sample composition views from which are just not allowing you to make a good tight model, then the cluster analysis can be a little bit more of advantage. The cluster analysis is designed that, for example, if you have in the vicinity of a certain result, 2 or more fitting, that it takes the average as a result, as shown here. So this is showing you the 5 different methods that are used by our instruments. The graphical user interface of the IR vision is a little bit different. It's not on this same standard as it was with the vapor pressure and the flash point, but it's still very intuitive. You have the main screen. Of course, when you want to do a measurement, you click on the measurement. Here you can set the different parameters, but basically what you need to do is press the start button and provide the sample, and afterwards you will get the results. The results has a header section where you have, for example, the typical features of the sample, like the density as well, and some other parameters that have been chosen, and then a list of the results which are given here. These yellow bars, which you see also overlaying some of the results, are giving you the typical range. So it gives you a good indication if you are out of a range or within the typical range. And you can, of course, flexibly set this. So this is also the summary of the IR vision. It comes in 3 different flavors. Basically, we have one dedicated to gasoline, one dedicated to diesel, and then also a pro version which combines the diesel and the gasoline, and also adds the jet fuel parameters. From the hardware, both instruments or all 3 instruments are the same. It's basically the calibration and the software which makes a little bit of difference here. I have mentioned this 2+1 cell design, which is laser regulated. Self-aligning mirrors, that's basically also something which is a quite unique feature. This FTIR Michelson interferometer needs to be very well aligned to get the optimal result, and that's what the self-aligning mirrors are doing. And with the latest version, we also optimized the signal-to-noise ratio by having a good heat source, a cool controlled detector and special electronics to optimize the signal-to-noise ratio. There are international standards and practices. This is for oxygenates, for benzene. That's basically the density meter standard which is in there. This is for biodiesel. Then corresponding EN standards. And then, of course, a wide range of standards we are correlating to. Correlation means these properties which we are predicting, and to create a database for prediction property, basically you are taking the results of the original standards, like here the NOC engine, and then you feed this information along with the spectrum into the instrument. And here are many more standards to which we can correlate because of the flexibility of this system, of this instrument. As long as the composition has something to do with a property, you may find features in the spectrum that you can correlate. So this database of fuels and the number of parameters which we can provide with the instrument is constantly growing. So finally, integration and automation with the cockpit. Cockpit is basically the Windows software which is combining all the vision instruments of Grabner instruments. You can use it to consolidate the results from multiple locations in one central lab. You can deploy different standard operating procedures, user roles, and just from a single place, and make sure that every laboratory you are working with who has the same instrument is using exactly the same methods and naming convention, user roles conventions, and so on. You can also check the calibration and calibration history of every instrument. You can configure and provide support to the VP Vision and also the FP Vision, which I didn't mention here. And I've mentioned also SQC and GLP compliance according to D6299.